you.
You're welcome.
So for my topic paper, I'm doing an article that talks about how seabirds are attracted to plastic because of the chemical compound.
Yeah, I heard about that. Yeah.
So I wanted to state the chemical formula for it in my paper, but when I Googled it online, I get 4 different versions and I don't know which one's the right one.
Okay. Do you remember what the chemical is?
I put it in my phone.
Dimethyl sulfide. It's going to be sulfide. It's going to be the second or the third. They're actually, and the last one. No. Sulfide is going to be the second or third. The other two are dimethyl sulfate.
Okay.
So either one of those, they're actually the same. It's just the brackets taken out, like that subscript, so you can see C2H6.
Okay.
But, yep.
All right. Thank you.
No problem. Methyl is just CH3.
Okay.
So dimethyl is 2 CH3s, and then sulfide is sulfur with an IDE. So that's the way the name comes about. Yeah, that was actually a really cool article. Or
Yeah,
I heard
I
about
liked
it on
it.
the radio. I didn't read the article. So. I have a pencil sharpener just like that. I think it's a great one.
Here's the thing. It was my fiance's, and I noticed it wasn't getting used.
Yeah.
So I just kind of went.
Yeah, it's really nice because it makes a sharp point and
Yep.
then a dull point too. So for the different.
Here's something funny. I needed a number 2 pencil to take an exam. So before I got these, I went to Walmart and I got these number 2 pencils. They look fat, and I was like, "What's going on with this?" But I like it. On the side of it's inscripted "My first pencil."
Oh yeah.
I must have got it for like
a kid one.
a kid one. I was
Yeah.
like, "This is kind of nice." But
I've
then
got some sketching pencils that are like super thick, so you can like get a good. If the angle's slightly different or something, it's
Whatever
really nice.
works.
Yeah. I'm not beyond stealing from my kid. He's got crayons that are like super thick like that too. Yeah.
I find that when I'm like thinking about something or get nervous, like some people smoke or whatever, I'll just do this. Yeah, I'm gonna sharpen that a little more. Yeah.
Here you go.
Pencil sharpen break.
Here's a little box.
Oh my god.
We actually have, like when teachers bring their kids in, we'll give them a box of pencils and they'll just sit and sharpen pencils. Like on a school outage day or whatever. Okay, well, welcome back to class, everyone. Hopefully things are moving along okay for you and you're keeping your head above water. I know this is really about as bad as it gets in terms of work for students and so forth at this point. So, yeah, I feel for you, is what I'm trying to say. We've got a few announcements and so forth. I guess, first off, any questions about anything? Well, actually, let me do a couple announcements first. They may clear up the questions. First off, clipping assignment is today. So we're going to discuss our clippings if we have found any interesting ones. but you have until midnight to submit it online. Several people have asked about what the deadline is. It's not at class, it's actually at midnight. It just makes my life easier. So if you haven't submitted yet, don't panic. You have until midnight. And that will be the last clipping for this semester, because we're basically at the end of the course, very, very close to it anyway. So that will be taken care of. Hopefully you found something, at least one interesting article, a couple interesting articles from the clippings. I'm always surprised that students, on the little yearly reviews and so forth, students actually say they like the clippings and like doing them because they like finding news articles and stuff. And I like it too. So that's why we still do it, I guess. So we'll do that. And then the other thing is the topic paper. I just want to remind everyone that I pushed the deadline for the topic paper until Friday night at midnight because actually the Monday, Wednesday class didn't want the topic paper and clipping due on the same day, so we pushed it to Friday. I'm not going to grade them before then anyway, so it doesn't make any difference to me. So you have until Friday at midnight to submit it. I'm not sure what Blackboard says as the due date, but it doesn't really matter. You can submit it. If you do have problems on Blackboard, and some people are reporting issues with Blackboard, just email it to me directly, and you'll be good. I'll reply and say that I got it, so that we know, and you should be good there. Okay. Other questions then? Anyone got anything eating away at them today? Yeah. I was watching everyone had headphones in at the beginning of class. I don't know why I thought of this, but it made me think of the old Walkman, Sony Walkman, like the very first one. And I think I'm going through a bit of nostalgia. I think the new old school Nintendo came out, and I really want to get a hold of one to play some of the old games. But I was thinking how excited I was when the Sony Walkman came out and I got one. I could walk to school and listen to music. That was huge those days. And I said, yeah, it's totally changed my life. I had a tape one. Flip the tape over. See, I'm old. It was a big discussion we had yesterday about how old I was. So, this bunch of students were talking about old cartoons, and I realized they were all animes that I watched growing up. So, Ghost in the Shell is coming out, I think. Okay, so enough of that distraction. Clippings. So I'm going to go first for the clipping articles, and the reason is because I want to introduce the extra credit for the exam as well. And it's all tied together. So I'm going to kill the lights here. See the screen a little better, it won't be quite as warm. Screw with me every time. Okay. So in the last couple weeks, a lot of news articles have been going on about fake news, like what is real news and what is fake news and things like that. And this has really caught my attention because as a scientist and a person, I deeply, deeply believe in the facts. Okay? And there are facts to things. You may not know what those are, but there are facts to things. And you can't just write a news article that completely goes against the facts. Okay? So for example, if I put a news article out that said Northern Kentucky University has 200,000 students, okay, and I just put that out as a news article and so forth, would people recognize that as fake news or not? Because that's not a true fact, by the way. We don't have 200,000 students by any means. So this has been going on, and I'm not talking about opinions and things like that, but just this idea of fake news. So it got me thinking, and I was thinking about whether or not I would be able to identify fake news or not. And I realized that sometimes I'm faked by the fake news. Like I don't understand. I click on it thinking that it's news, and then I realize it's not. So what I'd like you to do for your extra credit for the exam is basically answer these questions in like a one-page write-up, something like that, to submit so I know that you did it. First off, do you think you personally are able to tell the difference between what would be considered fake news and real news? I'm not talking sarcasm, but just like news that's not factually correct. And then to follow up with that, because we all have different opinions of ourselves, do you believe that general college students can tell the difference? So, like when I went to school, we learned about how to evaluate news sources and so forth. We learned like this would be someplace you could trust, this would be someplace you couldn't trust, and so forth. I don't think you guys do that anymore as students. I don't think that's part of the general curriculum going up through the schools and so forth. And it's gotten much, much more complicated over the years. You know, depending on where you get your news from. Google, for example, posted fake news the other day as real news. And it got promoted through their hot topics or whatever they call it and so forth. So do you think personally you can tell the difference between them? Do you think other college students can? And then I'd like you to post an example, so just a title or a URL link or something of one fake news story and one real news story. Okay. So see what the difference would be between them and so forth. And I guess I'd ask, does anyone, I don't know, do you guys think you can tell the difference between them?
On like Facebook and stuff like that, they have, I forgot exactly who made a video about it, but you're able to tell by the website URL.
Okay.
Because it's not actually from, an example like CNN.
Mm-hmm.
It'll have a little bit of a difference in the URL that doesn't actually go to like the website.
Yeah, I've noticed that. I got one the other day I clicked on from ESPN, and I thought it was an ESPN story, and then it said ESPN-magazine, like B.com or something, and it was slightly different. So yeah, that's a good point looking at that.
There are people on Facebook who take the Onion pretty
Yeah.
seriously.
Oh, absolutely.
And,
There's
like,
people that
it's-
absolutely believe the Onion.
It's just satirical.
It's not true, by the way. The Onion, what's another? I think The Duffel or something like that's another one. I don't know. I don't read it, but I heard the story. But there are several satirical ones out there that are so forth. A lot of people believe everything that's said on The Daily Show is true, which it's, in my opinion, it starts with fact and then gets adjusted. So I'm a huge fan of The Daily Show. So. Yeah, so I don't know whether or not we can tell the difference. And it's really important because your opinions and so forth are based on facts, right? The news stories you hear that you assume are correct affect what you think about things. So just take a look and see if you can find one that is not true and then one that is true, and we'll go forward from there. And that will be the extra credit.
Chemistry based.
No, it doesn't have to be chemistry based. It can be anything at all. It doesn't make any difference. Now, Facebook and Google have said that they're going to stop supporting these fake news sites. Apparently, there are certain news sites that do a lot of them by taking them out of the advertising on the sites. So you won't see like the fake news on the clicks for advertising and so forth is the idea there. But they can't take them out of the streams on Facebook, for example, because that's what people put in. So you can't just go in and say, hey, that's wrong. And who's to decide? I mean, there's obviously cases where it's purely false, purely true, but there's a lot more cases that are in the gray scale. So, okay. So that was my one. For an article, you can just search fake news and you'll find all kinds of articles right now. I kind of want to click on them, but I didn't look at them, so I'm scared. But here's, I don't know. Okay, so that's mine. Did anyone else find any interesting articles? Anything interesting out there? It's a boring week? Yeah.
They made a diamond nanothread, which is kind of like a lightweight sort of material that they're able to use for like the creation of planes and even like bulletproof vests. Because I know last year, and it even mentions in this that they made like carbon like nanothreads, but pretty much with the diamond nanothreads, it's just a whole bunch of carbon put together, so it's really, really cheap, and it's also like a renewable resource, so it's going to be even cheaper.
Wow, that's really cool. Yeah, that would be awesome. Diamond obviously is the hardest material that we know, so making stuff out of it would be very, very useful. It's also not super heavy by any means, so that's nice for planes and so forth. That's a good article. Anything else caught your eye? Okay, yeah.
Not as in-depth like that, but it was a story kind of relevant to now. They were talking about like Thanksgiving and how there's been that long myth about like tryptophan inside turkey and what exactly is it and how does it really work inside the body. And, it's not. It has nothing to do with it. It has everything to do with the quantity of food that someone eats that
Oh, really?
ends up making them more drowsy.
Sleepy?
So, yeah.
So tryptophan is the chemical that's been blamed for making you sleepy after eating Thanksgiving dinner for a long time. Apparently this article is saying it's not that.
Yeah, the
it's
New York-
just the fact you eat too much.
Yeah, the New York Times wrote a really good article, and they were basically saying that there is no higher levels of tryptophan inside turkey than in any other cut of meat. It's just obviously something that got popularized, and now after people gorge themselves, they get tired and they try to use that as the
Yeah,
excuse.
why wouldn't you use that as an excuse instead of they ate too much?
Right.
Everyone would feel better. If it's out of your control, it's the turkey's fault. So poor turkey, it's blamed for everything.
Doesn't one get pardoned every year or something
Yeah,
like that?
at the White House.
Yeah.
It's a tradition. The president pardons a turkey so he doesn't get killed.
So is that like killed forever, or is it just like until the day is over, then Pepper
No,
the
no,
farm
no, I
gets
think
to
he
pick
lives
him up?
forever on a farm out in the upper state.
Nice. They should do like a follow-up on that,
I'm
just to
not
find
sure
out
he
if like
really
they,
lives.
how they're doing.
Yeah, there's just a whole, what do you call a group of turkeys, a gaggle? A bunch of turkeys wandering around, a gang. Yeah, but they do part of their turkey every year, it's a tradition, the president does. Alright. Any other news stories? That's the first time we've ever discussed parting a turkey in class. Yeah. It is Thanksgiving time though. Every once in a while, I'll have an extra credit question of what's the best Thanksgiving food. And it always leads to arguments. The clear answer is mashed potatoes, by the way. No one else. I don't accept any other answer, so people get mad. So, there you go. Mashed potatoes are the best. Okay. I take it as that's enough for that. Anyone else got anything real quick, interesting they're dying to share? Okay. So that brings us back to why we're really here, and that's the chemistry. And we're discussing nuclear chemistry at this point, and I'm trying to see, I'm not sure that we're going to get much past nuclear chemistry in this course, and that's perfectly fine. But I do want to discuss, I mean, just on the drive in, I heard an interview with someone talking about Donald Trump, the president-elect, and the Iran deal, and whether or not he's going to try to adjust it, and whether Iran is going to allow that or not, or whether they're going to go back to actually enriching material for nuclear weapons. Okay, so, you know, we talk about this in class, but this is a real big deal in the world. I mean, between Iran and North Korea, and then just a couple days ago I heard that they're finally making a shield to put over the Chernobyl site so that the radioactive material isn't allowed to spread anymore. They're basically enclosing the whole thing. And then the Japanese meltdown, we're still dealing with the effects of that as well. So, you know, you may not think that this stuff is important, but in today's world it's really, really important. And it's going to become even more important as a bridge between traditional fuels, carbon-based fuels, and renewable energy sources. So if we have a time period there where we need to go between the two, nuclear energy is one of the possibilities. Germany, for example, basically outlawed carbon fuels a while ago. They cut off their amounts of carbon fuels. And when they did that, they started using nuclear fuel to replace it. And this has been a fairly common practice of other countries in the world. In trying to limit their fossil fuels, they're turning more to nuclear fuel. Personally, I think it's a good idea to do that, but most other people in the world don't. necessarily like the idea of going to a nuclear fuel source. Especially in the conversation where I just mentioned 2 of the 3 meltdowns of the world. We definitely don't want that to occur by any means. So when we're talking about radiation and nuclear reactions, we want to be able to describe them. And to do that, we have 3 basic types of radiation that we're going to discuss in class. And the 3 types, let me find my black marker here. The 3 types actually go by the names of alpha, beta, and gamma. Alpha being the first letter, second letter, and third letter of the Greek alphabet. It's the most boring labeling system ever. But this is the 3 types of radiation that we're going to talk about. There's a few other rarer ones, but we're not going to worry about them in terms of this class or anything. We'll mention neutron a little bit for nuclear power, but these are the ones we're going to concentrate on. Did I tell you guys the fish story with this?
No.
So a couple years ago, a student in the class wasn't familiar with the Greek alphabet, and they were having a really, really hard time remembering alpha, beta, and gamma. And they came up with the fact that this looks like a fish, this is a bee, and then this is the dead fish. And after that, they remembered it all the time. So alpha, beta, gamma, fish, bee, and dead fish as you go through it. So these are the particles that are being released when radiation occurs. So remember, radiation is when the nucleus breaks apart and a particle is being released out. Those are the 3 types of particles that we're going to talk about. The first one is actually shown here on this slide. This is an alpha particle. So an alpha particle is made up of 2 protons and 2 neutrons. That means that it has a mass of 4, has 2 protons. So the symbol for that is going to be 4,2He. 4,2He. 2 protons, the mass of 4, and the 2 protons define it as a helium here. And that is released from our nucleus. So if we start out here with uranium, we're losing 2 protons, so we're going down to 90. So the element itself is changing here. And we're changing from uranium to thorium. If you look to the periodic table, thorium is number 90Th on there. And we call this the daughter particle again. Mass-wise, we've lost 4 mass here, so we take 4 away from that as well. And this is really how we keep track of what goes on in our nuclear reactions. So, for example, alpha decay. Alpha decay is when an alpha particle is released. And to draw that out, what we do is we have to write the isotope we start with. Uranium, okay, 92 protons, a mass of 238. It undergoes decay, and we get a alpha particle out plus thorium-234. So this is what we call a nuclear equation. It's showing us what's occurring as this decay occurs. And again, this is the alpha particle. Alpha particles are always the helium nucleus. So 4,2He is the symbol for an alpha particle. Yeah?
You said that's the nuclear equation for
Yep.
decaying?
Yep. So this is the nuclear equation for uranium decay. Okay. For different isotopes, you're going to have different numbers and letters, but the same general idea is there. Now, to know that it's a good equation, you have to do 2 things. You have to make sure that the mass is the same on both sides, due to the law of conservation of mass, and also the number of protons are the same. So here we've got 238 as our mass, 4 and 234 add together to be 238. We have 92 for our number of protons, 2, and 90 gives us 92. So the numbers on the top have to be the same on both sides of the arrow. The number on the bottom has to be the same. And this holds true for all nuclear equations. And we can use that to make predictions as well. Let's say, for example, we have polonium-210. So polonium is number 84. This is an alpha emitter, so it's going to release 42Ag. What would the daughter particle be in that case? So on your paper, see if you can figure out what the daughter particle would be for this decay process. Okay, everyone got their ideas? Okay, so here we are. We've got a mass of 210 on our reactant side. On the product side, we've accounted for 4 of that mass. So that's going to leave us 206. Protons, we have 84. Then we have 2 accounted for. So we're going to have 82. And looking to the periodic table, Pb or lead. So once you understand that you've got to keep these numbers balanced, if I give you 2 out of the 3, you can always find the third. So I could keep this out and give you the other 2, and you'd have to figure out what type of particle it is or what we're starting with if I give you the 2 products and so on. A couple of hints for you here as you go through this. Well, one major one actually. Your particle that's being released in radiation always goes after the arrow. It never goes before the arrow. So radiation is always after the arrow as far as this class is concerned. So you know that that's always going to go there. That will help you with some of the wording and so forth. So alpha particle is 42Ag then. We could do the same with other particles. Here, for example, there's the uranium one drawn out. I don't know why I put that in there. Beta is the next one. Now, in beta decay, what actually occurs is an electron is released from the nucleus. And you may say to yourself, that doesn't make much sense. How is an electron released? Well, beta decay is actually the converting of a neutron to a proton plus an electron. So a neutron is changed to a proton and electron, and the electron is kicked out to the environment. So we lose one neutron and gain a proton in the process, and then the electron is kicked out as radiation. You can make sense of this if you look at the properties of a neutron. It has a mass of 1 and a charge of 0. Then you look at the proton and electron. Proton has a mass of 1, electron has a mass of 0. So that accounts for the 1 mass there of the neutron. And in terms of the charge, a proton is a +1, an electron is a -1. Add those together and you get a 0 charge overall. So you're actually still accounting for all the mass and the charge. But in this process, we've got to change from a neutron particle into 2 separate particles, one being electron and one being a proton. So the proton is what's being kicked out. And to show that, we use the symbol 0 -1 E. 0 because electrons have 0 mass. -1 because an electron is basically the opposite of a neutron. And then the E just because it's an electron. As you go through it.
How do you convert a neutron to a proton?
So it happens automatically. It's not like something that we do.
Okay.
Nature does it. And by saying that, I'm saying I don't know. Okay. In terms of what is happening at the most fundamental levels, I'm not sure anyone truly knows. But it is what occurs. We can see that it occurs. Okay. After the fact, we know that's what is actually occurring. Why and how it does it, I don't know. I can try and look it up, but I've tried before and I failed.
Yeah,
So.
it's not making sense to me. And I don't know how to like ask a question to, you
Yeah,
know.
no, absolutely. Think of it this way. Okay. So you have your neutron, and you have the mass of your neutron, and you have a positive and negative portions of it. Okay. But when you look at it from afar, it looks like it's balanced out at 0. Because from afar, they all kind of blend together. But if you got really close, maybe you would see these different portions. Then, during the decay, the negative portion leaves, and leaves behind something. And it has a mass of 1 and a positive charge. Okay? We would call that a proton, right? Mass of 1 and a positive charge is a proton. So the part that's keeping us from defining it as a proton to start with has left, and what's behind is being called a proton. Does that help at all?
So the electron is not leaving like a shell or anything
No,
like that? Okay,
no,
so
no,
valence
no,
shells
no.
have nothing to do?
No.
Okay.
Yeah. And that's a really, really important point, actually. In nuclear reactions, we're dealing with the nucleus itself, not the electrons on the outside and so forth. And this is why different isotopes have different properties, because they'll have the same electrons and everything, and chemically they'll act the same because that's controlled by the electrons. But in terms of the isotope nucleus itself, they're different, and therefore they act different. Yeah, this one's kind of confusing for a couple of reasons. One is which is the nucleus doesn't really have an electron. Right? So how is it leaving? Well, it's being created as it does it, is the idea there. Now, once you understand the symbol, you can do exactly the same thing. For example, here, if we look at this equation with an electron, we have 14, 6 carbon. So this is carbon 14, probably the most famous of all radioactive isotopes. It releases a beta particle plus the daughter particle is actually a nitrogen atom. So again here, we have 14 for our masses on our reactant side. We have 14 on our product side. And then the number of protons is tricky because we've got a negative involved, but we got 6 here. And then -1 plus 7 is 6. So you have to be careful there because it's a negative to make sure that it adds up. Yeah.
Okay, so will you always get, so is the product the C?
This is the reactant.
That's a reactant, and what are those?
These two are your products.
Products, okay. So you,
Bless you.
so you'll always have one product and one reactant, and then you have to figure out the other products, right?
Okay.
Like if you was like ask a question, you would say,
Yeah.
I have C 14-6, and then the line with the reactant.
I've got some example problems in a
Okay.
minute. Perfectly
Okay.
fine. But to answer your question, what?
Because like how will we know what the product is?
So the product is after the event. So the product forms, the reaction yields this, those types of things. So the product is after. Okay? And then the starting material or the reactant, not reactant, reacted is the before part. So if I say carbon-14 is a beta emitter, what is the product? Or what is the daughter particle? Then you know that's going to be this.
And you said it is a what mineral? Beta. Oh.
A beta emitter, which means that it's giving up beta particles.
And the beta, what did you say?
Beta particle?
Beta particle would always be E0 and then 1.
Yep.
Just like the other one you was doing was, I think it was
4,2 He.
Yeah,
Yep.
4,2 He.
Yeah, and they are always that. That's the
Okay.
key thing to remember. Yeah.
So we'll memorize what those three are, so
Mm-hmm.
in the event that obviously we get asked a question, we'll know, all right, we're looking for alpha, we're looking for beta, we're looking for gamma, and then obviously kind of algebraically plug and chug.
Yes.
Okay.
Yeah, that's the idea. Let's take a look at the last one, and then we'll do some examples, and we'll see the different types of questions. There's really 3 different types of questions I might ask, so we'll do one of each, and then we'll see where we stand. So beta, then, is always 0 minus 1e. It's an electron. So anytime you've got a beta emitter, an electron is being kicked out. The final one is gamma. Now gamma is a bit different in the fact that gamma is simply energy. Okay, this may be X-rays, this may be microwaves, this may be light. Any of these types of things is just energy. So you start out with something and you end up with the same thing, but lower in energy. So there's no actual particle, physical particle leaving. Just think of it as light leaving or energy leaving. So to describe gamma, the symbol we use is 0, 0, gamma. So there's not going to be any change with the mass, and there's not going to be any change with the number of protons. So it's also not going to change your chemical symbol. Gamma really is just describing energy loss. So that you guys are aware of it, what we do is we put a star next to the higher energy and no star next to the lower energy. So beforehand has a star, which means it has extra energy, and then it loses the star, denoting that it lost the energy. That's not something I normally ask questions about and so forth, but you may see it at some point. So I just wanted to mention it to you there. So gamma is really the boringest of all of our equations. If, for example, cobalt-60 is a gamma emitter, and I don't know that it is, but we'll just say it is. Cobalt is number 27. 0, 0 gamma plus, what would the daughter particle be? Well, it's just 60, 27, okay, because it's 0 and 0, so there's no change as you go through it. So it's just energy there. You're not taking any protons away, neutrons away, or electrons, or anything like that. It's just, there we are. And that's the gamma one. So that's the third one.
So they'll always be the same on both ends?
For gamma? Yeah.
Okay.
So up here at the top then is an example of it. Iodine-125 releases gamma radiation, and you get iodine-125 out. It's just the way that it goes about it. Now, one other thing I should mention with gamma, gamma rarely occurs all by itself. Most of the time, gamma radiation is paired with another form of radiation. So here, for example, is, cobalt-60. Okay, cobalt-60 giving up gamma radiation and then also a beta. So in that case, it's giving up two things. It's giving up a beta and a gamma. I'm not going to ask you guys to do those or anything, but just so you know, the rules still hold true. So 60 is your mass, 0 plus, or 60 plus 0 plus 0 is 60, 27, 28 plus negative 1 is 27, plus 0 is 27. So the whole idea of balancing still holds true when you have multiple components, but it's a little more than we need to do for here. So let's try this one. Plutonium-239 decays to release an alpha particle plus what daughter particle? Let's take a minute, or probably a little less than a minute. Okay. So we start with 239 for our mass, 94 protons. We're giving up an alpha particle. So we're looking for our daughter particle here. 239 there. 4 has been accounted for so far. So this is going to be 235. 94 and 2 is going to be 92. And that's then uranium. Uranium is number 92. Does that make sense for everyone?
How are you getting, like, how are you converting this to uranium? Is that just because that's what it equals, that's the closest thing that it equals?
So here we start with 94, and then we've accounted for 2 protons, so this ends up being 92.
Okay, since that's.
So then we look to see what element has 92 protons, and that's going to be uranium. Yeah.
So then you don't go by the mass of the top?
Nope, you don't go by the mass. The identity of an element is always defined by the number of protons. And that's actually important because, like, hydrogen 3, you've got hydrogen 1, hydrogen 2, hydrogen 3. They all have different masses, but they're all hydrogen.
Okay.
And they do act differently. This is the only one that's radioactive. But that being said, they're all hydrogens. Yeah.
This may be a dumb question, but what would you have to do to your reactant to actually break that down? Like, what is actually physically happening?
To break hydrogen 3 down? Like,
No, not on that one, on the top one. Yeah.
this one?
Right.
For this to occur, it actually just occurs on its own.
Okay.
It's spontaneous. So almost all of the examples we talk about here, alpha, beta, and gamma in particular, are all spontaneous emissions. So given a certain amount of time, it will occur.
So it's like these little discs.
Now, yep. Now that amount of time may be a billionth of a second, or it may be a billion years. It differs. Every one, we'll talk about that. It's called half-life, but it will occur eventually. You can force some radioactive decays, and that's what we do in nuclear power plants. We actually force it to occur.
Speed the process.
Yeah, speed the process up, and then with that, in that case, we shoot a neutron into it and change the isotope to a radioactive one, and then that cascades down.
Oh, wow.
Goes down. It's actually really, the cascade effect is really big. I've got a slide of it later. But. Okay, let's try this one. Potassium-42. This would be what makes our bananas radioactive. Is a beta emitter. So let's see if we can figure out what the daughter particle would be in this case. Okay, everyone got their ideas? Okay, so here again, we have 42 for our mass. We've got 0 at this point, so that leaves us with 42 for our new mass. We have 19 for our number of protons and a -1. So whatever number we come up with has to be added to -1 to get 19. So that's going to be 20. And the symbol for that is going to be calcium. This is the hardest thing of all of these nuclear equations, is the fact that it's a negative number there. And that means that this is not 18, it's actually 20. That trips up 30% of the students on a routine basis. So I always say, once you've got it done, go back and say 20 plus a -1 is 19, just to double check yourself. I can't even imagine how many times I've seen students miss that for that very simple reason. I didn't make it a negative, so don't blame me. But yep, there you go. Questions about that? No? Okay. Let's try a different type here. Let's do the first one. Technetium-99 is a beta emitter. What is the daughter particle that forms in the process? Say 10, 15 seconds. Okay, so in this case, since it's not given to you as an equation, you have to figure out what goes where. Now, technetium-99 is a beta emitter, which means that technetium-99 breaks down and emits a beta particle. So technetium-99 is going to be our starting material, because that's what is being broken down. And it says that it is emitting a beta particle. So we know a beta particle is being produced, and that then leaves us with only the daughter particle defined. And in this case, it's going to be 9944. Oh, ruthenium. 9944. Everyone agree with that? Questions? Okay. So let's finish up and try the last one. What type of decay occurs when radon-226, oh shoot, I did that again. Ra-226 decays to form Rn-222? A few more seconds. Okay. Any questions before I start writing this one on the board? Okay, so with this one, the real trick is figuring out what is a reactant and what is a product. So are we starting with RA or RN? RA. because Ra is decay, it decays. So that is what is being broken apart. So that's going to be 226 Ra, 88. And then it's going to decay to form 222, 86 Rn plus
Alpha 4, 2, HE.
4, 2, He, which is an alpha particle. No. Yeah.
So why is the RN and HE reversed?
It doesn't matter.
Okay,
You can do it the other way. I just did it that way because we knew this first.
okay.
That's the only reason. Yeah, with pluses, you can reorder them however you want. It makes no difference. You just can't move something from this side to this side because this is like before and after.
Okay.
Okay, yeah.
So when we're answering this on a test, do you want us to like draw a symbol, or do you want us to write it out?
Makes
Does
no
it-
difference to me. No differences to me. So the way the question is worded, you can just write alpha. And after you do some of these, you're going to be able to look at this one and know that it's just alpha, so you can just write alpha. That's perfectly fine. You could write 4, 2, HE. That'd be fine too. It really doesn't matter at all. It's, as long as you can figure out what it is, then you should be good. Any other questions? Is this stuff making sense? Yeah.
Can you do one? I know you said it was one, but can you do one like gamma decay?
Oh, of course. Of course. I don't think it's boring. But that's just me. I'm kind of a special case. Okay, so the wording of something for a gamma decay would be like, I'm just going to make something up here. So actually, let me change one. I don't like the element. I'd rather have isotope there. Okay. What isotope will decay to form chlorine-40 through gamma decay? So on your paper, write out an equation for this. Okay, so the equation for this is going to be, we know that we're making gamma, so that's going to be 0, 0, and this. And we're also forming 40, 17 Cl. So what isotope will decay to form that? Well, 40 plus 0 is going to be 40, 17 plus 0 is 17, which is also Cl. So the isotope that will decay to form chlorine-40 through gamma decay is chlorine-40. Yep. Yeah, it's going to always be like that. Because it's 0, 0, so nothing's going to change as you go through it. But I'm glad you asked, because that gave me a chance to have a question where you need to find the starting one. Okay, any other questions? Okay, So that's how we describe nuclear equations and keeping track of things. So if you know, for example, what the daughter particle is and the type of radiation, you can figure out what the starting isotope is. If you know the starting isotope and the type of radiation, you can find the daughter particle. Given 2 out of the 3, you can always find the third. And that's kind of the approach we'll take. Now there are a few other types of radiation, as I mentioned. You may see them from time to time. We're not going to talk about them at all. Positron emission gives off what's called a positron. It's the opposite of an electron. Don't worry about it. And electron capture is another one. The final one that we will mention briefly a little bit later on is neutron. And in that case, you're using a neutron to actually cause radiation decay and so forth. And we'll talk about that because that's what happens in nuclear power plants and nuclear weapons, actually. We'll talk about those later on. Yeah?
Okay, I'm still like
Yeah, I
caught
know.
on the beta emission.
Yeah.
So is a neutron itself like 2 different things? Like a positive and a negative thing put together? And so whenever it like releases
No,
no?
not
Okay,
really.
sorry.
No, it's fine. You're thinking about it, but the problem is this. In chemistry, we have, for historical reasons, but also for practical reasons, defined the most basic particles as a proton, neutron, and electron. And we treat them as if they are the thing. But that is not actually true. So protons, neutrons, electrons are made up of other things called subatomic particles, other types of subatomic particles. You may have heard of some of them like neutrinos, quarks, leptons, neutrinos. I said that twice. But there are several of them that make it up. Now in chemistry, we don't deal with those because the fundamental properties of elements are not directly affected by them. They're made up of them as you go up the scale, but you don't have to go back down to them to understand it. Now, a neutron is not one thing. Okay, it's actually made up of these smaller things, and I'm sure the answer to your question has to do with the smaller things in some degree, but honestly, I'm not sure anyone truly knows.
Right. It just like, it doesn't make sense to me, and it's really
It bothers you, I can
like
tell.
why does losing an electron give you a proton? Like
Well, losing the properties of an electron
yeah.
gives you the properties of a proton.
So it's
Maybe a better way to think of it.
yeah. Okay. So it's just the properties that are changed. No. Never mind.
No.
It's I know it's so frustrating. I just don't know how to ask.
No.
question.
Okay, however you ask, I'm not going to be able to answer it.
Okay.
Okay? Because I completely understand your issue here.
Okay.
The way I think of it is this. If you have yellow and blue overlapping, you have green, right?
Yeah.
Take the yellow away, what color do you have? Blue. Okay?
Okay.
Now, when they're overlapping like that, we call it green. But the green is actually made up of 2 different components. Like a neutron is made up of different components. Take one of those components away and you're left with something, and we just call it something else. Now, scientifically, that's not 100% correct in any way, shape, or form, but that's the way I've come to think of it.
Okay. Yeah, that helps for sure.
Okay, so that is how we describe reactions that occur. There are a few other properties that we need to discuss to understand our practical applications and so forth. And the first of these is half-life. So half-life is the rate at which materials decay. So all of these types of radiations are spontaneous decays, and that means they're just going to occur over time, but the speed at which they decay is different for every isotope. It's characteristic for that isotope. One isotope will always decay at the same rate, but isotope to isotope, they're going to have very, very differing rates. So for example, technetium, which is used in medical applications, has a half-life of 6 hours. So if a doctor wants to use it, he has to call and have the technetium sent to him per use. He can't just keep it in his stockroom because over a day, a lot of your material has decayed away to unuseful stuff. On the other hand, uranium-235 has a half-life of 7 times 10 to the 8th years. So I think that's in the billions of years there. So radioactive waste actually contains some uranium-235. So if we want to wait until all of the radioactive waste is going to decay, it's going to be in the hundreds of billions of years, actually, as it goes through it. So each isotope then has a different time period. And because of those time periods, you can do different things with it. Tritium, for example, is 12 years. The radioactive dating that tritium does is in wines. So if you buy like super, super old, expensive wines, and I'm not in this world at all, so don't pretend like I am, where you're paying tens of thousands of dollars or millions of dollars for bottles of wine, one of the things they'll do is they sample the air on the inside of the bottle, they draw some of the air out, and then they look at how much tritium is in there. And from that, you can actually figure out how old a bottle of wine is. Because when it's capped, the tritium is trapped in there, and then, or corked. The tritium is trapped in there and it can't get out. So there's all different types of things and practical applications, but to understand it, you have to understand half-life. Now, we are going to take a very simplistic approach to half-life, and it is simply in the definition itself. In the amount of time of a half-life, half of your material will decay. So if I start with 100 grams of something, after one half-life, half of that is going to disappear. So now I'm going to have 50 grams. So half of it disappears. Then, if I wait one more half-life, half of that amount is going to disappear. So now I'm down to 25 grams. And it gets cut in half every time. So one more half-life is going to be 12.5 grams, and so forth and so on. So every half-life you have, the amount is halved as you go through it. Now, this half-life is different time periods. Let's say, for example, that it is, well, technetium, it makes a nice one. That means that going from 100 grams to 50 grams is about 6 hours. Going from 50 grams to 25 grams is also 6 hours. So if you want a 100-gram sample to decay to 25, that's going to be 12 hours. 12 hours. It's going to be 2 half-lives, where the half-life is defined as 6 hours.
So is that a given for all isotopes, or for the half-lives?
All isotopes, the half-lives act exactly the same. The only difference is the amount of time that a half-life is.
Okay.
And the half-life time is not something that you're ever going to know. It's always going to have to be given to you, because it's literally different for everyone.
Okay.
So you don't need to know like what isotopes are radioactive, and also you don't need to know the half-lives of them and so forth. It's going to be given to you. Or everything else is going to be given to you for you to figure out what the half-life is. Okay, let's try a problem once. How many half-lives have passed if a 400-gram sample decays to 25 grams? Everyone got their ideas? Okay. So I'm going to start with 400 grams. One half-life is going to take me down to 200 grams. Another is going to take me to 100 grams, to 50 grams, to 25 grams. So it's going to take 1, 2, 3, 4 half-lives. 4 half-lives to get down to 25 grams. Questions about that? Okay. Now this is the way that we are going to do it as a class. There's a couple things you need to know about this. This works when you have whole number half-lives. So 1 half-life, 2 half-lives, 3 half-lives. It doesn't work if you have 3.5 half-lives. 3.25 half-lives or whatever. So we will only work with whole number half-lives in this class. Everything will work out perfectly. Also, because of that, you do not need the mathematical explanation of half-lives more than just dividing by 2 or multiplying by 2. If you look online and so forth, there is a mathematical equation you can use to calculate half-lives and so forth. We are not doing that in this class. If you want to use it, by all means, please feel free. It works perfectly fine, but we're not getting into the math of that at all. Okay, so we can just divide or multiply by 2. Okay, everyone good with this one? Okay, let's see what would happen if I change this to say how many days have passed if a 400 gram sample decays to 25 grams and the half-life is 3 days.
To get to 25?
To get to 25 grams again.
Oh, okay. So you consider 1 day as going to 200?
Well, that is 1 half-life.
Oh, yeah, 1 half-life.
1 half-life. Yep, which is how long? Not 1 day. It's
1 hour. No, 6 hours.
3 days.
3 days.
Oh,
3 days is this problem. And a half-life is 6 hours. 3 days, yeah. 6 hours corresponds to the technetium.
Oh, I didn't see what it says half-life. Okay.
And a half-life is 3 days.
What is that after 25 grams? That's just the,
There you go. Better.
okay.
That was the cross out of the old question mark. Anyway. Okay, so to do this problem, we first figure out how many half-lives it's going to take to get down to 25 grams, and that's 4. So 4 half-lives, and if each half-life is 3 days, you multiply the 2 together, and 12 days would pass. 12 days would pass. Okay. So when you ask for a time period like this, just figure out how many half-lives have passed, and then how long each half-life is. Now this is very, very, very common in carbon dating. So one of the primary things is carbon-14 here is used in carbon dating. So they figure out how much carbon has decayed down, and then from that they can figure out how long ago the sample was taken, or how long ago the tree was burned, or the cotton was woven, or things like that.
So would that be the same if you asked a question on how many hours?
Yep.
Okay.
So how many hours? In this case, you would have to take the 12 days times 24 hours. But if the half-life was already in hours, it would just be a multiply.
Okay.
Years would be the same too. Let's do one more problem. Going the other direction. Or just my brain just large was a starting sample if 40 grams remains after 6 half-lives. So how large was the starting sample if 40 grams remains after 6 half-lives? Okay, everyone got their ideas? A few people punching it out still, but okay. So if 40 grams remains after 6 half-lives, we have to go backwards in time. So instead of dividing by 2, we're going to double it. So if we go back 1 half-life, it would have had 80 grams. The second half-life would be 160. The third would be 320. This is getting kind of crazy, I guess. I need to pick a smaller number. 640, 1280, 1560. No, 2560. 5, 6. So 2,560 grams would have been your starting sample size. So here, when you're going backwards in time, you're actually multiplying by 2 instead of dividing by 2. Okay, one more and then we'll give up for the day. The last one here. How long has passed, I should say if an isotope with a half-life of 2 days has decayed to 25% remaining? Just to make sure everyone's getting started, you're going to start out with 100% and then figure out how long it's taken to get down to 25%. So to run through this, we're going to start out at 100%. We need to figure out how many half-lives have passed to get down to 25%. Well, the first half-life is going to take us to 50%. The second half-life will then take us to 25%. So 2 half-lives have passed. If each half-life is 2 days, that means 4 days have gone by. So 4 days would be how long it's taken. Good? You guys are all packing up. I assume it's good. Okay. Go. Enjoy your weekend. The last weekend before Thanksgiving, I think. Thanksgiving's next week, right?
Yep.
Already? Yeah. Mashed potatoes.
We have an exam the week after Thanksgiving. Right?
Yes.
Okay.
Yes. The Tuesday after Thanksgiving.
Okay.
Oh wait, is that right? Or is it the next week? I think it's one more week. So after Thanksgiving, we do not have an exam. It's the week after it.
Okay. So the first week of Thanksgiving.
First week of December. December 6th is what it would be for this class. We have 3 more lectures. So 1 next week and then 2 the week after Thanksgiving.
So are we gonna get to chapter 8?
Okay.
Like, I'm not, chapter 8, I'm not certain, but I'm not gonna start a new chapter with only one lecture left. Or
Okay.
something like that, so we'll have to see. I really don't think we will. Hey, what's up?
This, the final exam.
It is. Yep. Yep. Use your old exams to study for the. Cool.
Have a good day.
Yeah, you too. See you later. Go hit the lights, everyone.